you want to talk about isolation transformers and how they compare?
Well, that's the big benefit of an isolation transformer, is that it does the same job much more efficiently and much more reliably. Because there are ways, even when a galvanic isolator is working properly, where it can be essentially overcome, and then you get galvanic currents coming through that line. The isolation transformer is basically pretty much bulletproof. It breaks that circuit to shore, and then it creates a new AC circuit on the boat. So then if you get any fault currents on the boat, the path for the fault current is always back to the source of power. And since the source of power on the boat is the isolation transformer, it's going to go back to the isolation transformer, and it's not going to go in the water or go anywhere else. It's basically going to be contained within the boat. So it gets rid of the galvanic corrosion issues, and it creates a much safer environment on the boat. But of course, they're fairly expensive, and some of them are pretty heavy, and they can be noisy, some of the older ones. So there's always downsides to these technologies.
Yeah.
You know what we've done for years on our boat? Most modern marine battery chargers will accept a universal input. Just like you can go anywhere in the world and you can plug in your cell phone charger or your laptop charger. Well, the most modern battery chargers are the same. You can plug them in anywhere in the world. So if you take all of your AC loads and you put them on an inverter, or if you've got high loads, stacked inverters, 2 or 3 inverters, and you run the entire boat's AC loads off the inverters, and then you have one of these universal battery chargers. You can go anywhere in the world, plug in, the battery charger will feed through the batteries to the inverter and run your AC stuff. If the AC loads exceed what the battery charger can feed from shore, they just suck off the batteries and discharge the batteries a little bit. And then when the AC loads go down, the battery charger will recharge the batteries, they'll catch up. So effectively, you microcycle the batteries and you run all of the onboard AC equipment off the inverters, and you have no hardwired connection between shore power and the boat's AC circuits, because you're going to the battery charger, from the battery charger to the batteries, from the batteries to the inverter, and from the inverters to the boat's AC systems. And you can run, nowadays, you can stack inverters to maybe 20 kilowatts. I mean, you can run a ton of air conditioning, for example. And if you don't mind me rambling on for a moment, let's say we have a whole bunch of air conditioning on the boat, and over the course of the day, the total load is 72 kilowatt hours. So that's over 24 hours. If we divide the 72 kilowatt hours by 24 hours, we discover the average load is 3 kilowatts. So all we need to keep up with that is a battery charger that can put 3 kilowatts into the batteries, which you can easily get with a 50 amp short cord. And if you really want to push your luck, you can get close to it with a 30 amp short cord. And in the meantime, when the load is high on the AC side, the batteries will get discharged. And when the load goes down, they'll get recharged. And over the course of the day, it will all balance out. Yeah, and we've done that for 15, 20 years on our boats. And it works great.
Yeah, we do those conversions for European boats. The only challenge, and you brought it, is that when you're in colder climates where you're using, and here it's not uncommon to have 2 heaters, 3 heaters, pulling 10, 11 amps per circuit per heater at 120, you can easily offset the normal battery chargers, because battery chargers are going to come pretty much the largest, unless you stack them, are 100 amps at 24 volts. And that's going to be something, but not enough. So then you end up stacking more of them to offset. So it gets tricky where you need constant heat. That's the only challenge. In milder climates, like you're in Europe and stuff like that, where it doesn't get too cold and you're not running too much heat too long, it might be easier. But yeah, it's a limitation, but a great solution though. Great solution to do it via battery chargers to inverters. Yeah, very, very neat.
Yep. It works well.
Yeah. So the isolation transformer, just to recap on that. So the other one too, we also talked about also the fact that it sorts out polarity issues, which is a real threat in destination marinas where it does happen, where the neutral and the hot are reversed. That's also going to solve that problem. So you get two wins with an isolation transformer. You talked about the galvanic protection, and then also obviously the reverse polarity. And I when I look at those things, and you're right, the cons are absolutely the price, the weight, the volume it takes, and the sound. Some of them. So if you generally with the bigger boats, the trawlers, once you get around 40, 45, 50. For sure, 60 feet, they're going to have isolation transformers. They're going to have one. It's just the smaller boats, the 30, 40 footer, is there a place, and are you willing to spend the money, the cost, and are you going to get a boost transformer? That's the other thing too, which makes sense in destination marinas. So those are all different factors at play on the shore power. One last question on grounding, and I get this all the time
So
from the
on
channel.
the isolation transformers, we do have high frequency transformers in the marketplace now, which are a lot lighter. And then we've got, just recently, we've seen the introduction of toroidal transformers that you can tell them because they're kind of round like a donut. Which
tell us about those ones.
What's that?
I said, yes, tell us a little bit about those ones. I haven't seen that one.
I think they're in Connecticut.
Okay.
They're fairly recent. They don't comply with some of the ABC requirements in terms of shielding between the primary and secondary windings. They can't because of the way they're built. So fundamentally, I think we're likely to see a change in ABYC standards to catch up with the technology, but I can't say that for sure. But they certainly are pretty good as well, and they're lighter and smaller. So we are seeing some alternative technologies in terms of isolation transformers that are pretty effective and do affect the same job, but don't necessarily meet all of the prescriptions of the ABYC standard, which was written 20, 30 years ago, before any of these technologies were available.
What's your thought on the pros and cons versus high frequency to low frequency for the isolation transformer? What's your trade-off in your mind?
Sorry, Jeff, you're very faint on what?
The trade-off. Yeah, I was wondering, what's the trade-off in your mind between the high frequency and low frequency isolation transformers?
I think it's all largely a matter of weight. I mean, personally speaking, I don't care how it's built as long as it does the job. The high frequency, they also, it took several years before the ABYC caught up with them. Because they're built very differently to a traditional transformer, and the standard was written around traditional transformers, which is interesting because one of the things that we've tried over the years is to make these standards performance standards rather than construction standards. Because if you write a construction standard, something has to be built this way, and then technology changes, the standard is basically out of date, and it becomes an obstacle towards adoption of the new technology. So if you write a performance standard, you simply say that the transformer or whatever it is has to be able to do these things and do it safely. And I think that's a good example of where we wrote a construction standard, which is basically an obstacle to getting new technology onto our boats. And we're going to have to change it over time and make it more of a performance standard.
Okay, good point. All right. Anything else you want to share on isolation transformer before we close off on grounds? I just want to last one question on grounds.
I don't think so. This is an issue that you get a lot of emails and feedback, and I do too. It's very confusing just because there's so many different grounding and bonding circuits on a boat. And it's hard to know which one is basically driving the bus, if you like, at any given point in time. But it's also essential to figure that out so that you make sure the conductor is large enough to carry the worst case fault current it's going to see.
Yeah, my advice on that is to draw it out. Don't think that it's right. And over time, create a schematic for your boat and understand what size circuits are connected to what. You want to obviously avoid the loops, which can happen if you get too happy-go-lucky and you're just connecting everything to everything. I always think about, a tree, with the roots in the ground, or one trunk. And as it goes out, one trunk to many trunks, and then to branch circuits, and smaller as the way I look at it. But the challenge and the question I was going to ask you, Nigel, was, most boats don't have even a ground labeled on the boat. Most, other than AC, on the DC side, it's going to be called a DC negative. It's going to be a distribution. But I think the challenge is also that the builders are stacking multiple things. And I do the same thing. We're having one device that does multiple things. But when we look at schematics online, they're seeing, as you talked about, an AC grounding bus, an RF grounding bus, maybe a grounding bus for the through hulls and on all underwater metals. There's going to have another one that's DC grounding. And then they're going to be like, well, what's the connection to ground? Is it going through the engine? Is it going through a plate? How am I going to do my connection to the ground? Do you want to talk a little bit about sort of like lessons learned from your side on the implementation of what the ideal is? Because I think that's the largest, hardest part is there's no place on a boat that even has those labels. People don't know where to start. They have to almost interpret what they're seeing. What are your thoughts on that?
So I think conceptually it helps to separate all the DC negatives that go to what the ABYC likes to call a DC main negative bus. So that's the negative side of the DC circuits. And they all end up at the DC main negative bus. And then conceptually, we have the grounding bus, to which we tie the AC grounding conductors and any bonding conductors for lightning or corrosion protection, or any DC grounding conductors. Those are not the DC negative. They're the ones that are attached to the case of the inverter, for example. So we conceptually, we have these two separate buses. In practice, if we have a boat on which the DC negative side is grounded, which the vast majority of our boats, that's how they're wired, then we can fuse those two buses, so we don't need two separate buses. So we can take those conceptually separate buses and turn them into one bus, and that's what I have on my boat. On the other hand, if we have a boat with an isolated ground, an isolated negative side on the DC side, which we do have on some boats, we call it isolated or floating ground. So then the DC negative side is deliberately not wired to the boat's grounding circuits.
Right.
So then we absolutely do have to have the two separate bus bars. We have the DC main negative bus, which is where all the DC negatives go. And then we have the grounding bus, which is where all the grounding and the bonding and the lightning protection goes. And those two have to be not only physically separate, but they have to be electrically separate. And that way the DC system itself is now a floating system on the boat. It has no connection to the grounding system or to the water anywhere on the boat. And in fact, typically, if you're going to install one of those systems, you want a device which can detect if that isolation gets voided in some way, and will alert you to the fact that the isolation has been voided. Normally speaking, we only put those kind of systems on metal boats as an additional corrosion prevention measure. And in fact, they do that in Europe way more than it's done in the States. And I think the ABYC would argue that in actual fact, it doesn't provide any more corrosion prevention than a grounded system, if a grounded system is installed properly.
Okay. Yeah, that's a good little recap.
Is that
I mean,
too much in one
yeah,
flow?
that's good. No, that's good. I mean, it's a hard topic, right? I mean, you're right. I mean, I think the term you use is conceptual, right? Like you're right. It's these on the piece of paper, you might they're separated, but in reality on a boat, you're going to have these multiple connectors that do various things, most likely all connected to one place.
Yeah, another way to think of this is the all of the conductors that are attached to the DC main negative bus are current carrying. They're the negative conductors. They're the return path on those circuits. All of the conductors that are attached to the grounding bus are normally non-current carrying. They only carry, other than a very small currents we might see with galvanic circuits, but we're talking milliamps, a few milliamps. So the one bus is dealing with the current carrying circuits, and the other bus is dealing with the non-current carrying circuits. And then those non-current carrying circuits, or the grounding and the bonding circuits, the only time they carry current is if there's a fault in the system. And then those two buses can, as I said before, can be combined on a boat with a grounded DC negative. But conceptually, the big difference is between those that are current carrying and those which are not.
So if you're curious, again, go on our website and find out more answers and solutions with this sort of setup.
And thanks for asking. And thanks for all of you for listening and tuning in.